Okay, this is another example of a pension question. This time we're looking for the pension payment. We're given that we've invested a lump sum of 500,000. We have an annual rate again of 4.2%, and we want to know what monthly pension payment would this provide for 25 years. So there's a couple of things going on here. You definitely should have looked at the previous video and working out what fund you would need. So this time we have the fund, but it makes it a lot easier for me to explain this if you've understood the last video. Okay, so I'll put a link to that last video up there, and definitely check that out quickly first. So if you do understand that and you've done it, you'll remember that again we're going to talk about taking the payment from the start of every year. So what we're going to say is that we want our first payment to come out on, say, the 1st of January again, right? So the 1st of January we take out some payment X, or sorry, the very first payment X. Then 30 days passes, the next month we want some other payment X again, but these two X's are the same because we want our monthly payment to be the same, so we're on to the 1st of February, right? And then we're on to, so on, the 1st of March. So baby steps here. And some other payment amount X. So all these payments, right? Now what we figured out in the last video was we could figure out the present value of all these payments. We said we knew the payment in the last video, and we said the payment had some final value equal to its present value. This is the standard complex compound interest formula. So we knew something like this, and we knew our payment, our present value was each money we had to have in there. So actually we're going to work out a present value for each of these payments. So how much needs to be in there for each one? Well, the first one is just X. I mean, the first payment needs to be just there. It's not going to accrue any interest. It needs to be there on day one. What about the 1st of February? Well, the 1st of February, that payment's going to be in there for 1 month. Now, one quick thing we need to spot is this. We need to get 4.2%, which is an annual rate, to a monthly rate. Okay, now I know that's equivalent to a monthly rate of 0.3434%. If you don't know how to change monthly or yearly to monthly, check out this video here, and there's a link here to this one, and that will explain that quickly. Just to save time, I have already done this one before. So 0.3434%, and of course need that in a decimal, which is 0.003434. Okay, so we know that we come back to our payment here on the 1st of February. It has a present value, by rearranging this formula, of the final value, which we don't know what it's going to come out, the final value, which effectively is X, right, and over 1 point, and the monthly interest rate now 0.003434, and that's accruing 1 month interest. So whatever money we put in there now, right, I suppose I can change this final value to X because that's what we want to take out. We want to take out that final value. So we want to put in some amount of money now that's going to have this value X. So we're looking for the present value now. Okay, similarly on the next one, this is exactly the same in the last video. What money do we have to have in there now? For this payment, the payment's going to be X. It's going to have a present value now divided by this. Now, 25 years, how many months is that? What's this going to go up to, right? Well, it's going to go up to 25 by 12, and that is going to be 300 months. But I want you to know this, is that we also stop this one at actually 299. Why? Well, the first payment in there, this is the first term. There's going to be 300 payments, okay? The very first payment accrued its present value was its final value. They were the same thing. We needed that money in there on the day. The second payment had 1 month's interest accruing. The third payment had 2 months. So the very last payment, similarly, will be in there for 299 months. That's its present value. Okay, so when we look at all these, like the last one, we have to add all of these together. Being the very first one, right, which is going to be X plus the next payment, which is going to be x over 1.003434 to the 1, plus x over, this is the next one. Now remember, the last time we did this, we knew the payment each time at the top, but this time we don't. That's why they're all x's, okay? Up to the very last payment x that's going to go out. And that has a present value now of 1.003434. And of course, that's in there for 299 months. So it's not in there for 300, remember, because if it's in there for 25 years and we take it out at the start of each month, we're taking it out a month before 25 years is up, which is 299. Okay. So we have all this geometric series looking stuff here, except the only difference between the last question, or the first example for this when we were calculating the pension fund needed, is we actually knew all these amounts x. We knew we wanted in pension per year or per month, whatever it was. This time we don't know what the payment is, but we know the present value of all these payments, and we know they should all add up to 500,000. Now what I'm going to do now is I'm going to factor an x out from this left hand side, which is going to give me something like this: 1 plus 1 over 1.003434 to the 1, plus 1 over 1.003434 to the 2, all the way up to 1 over 1.003434 to the 299. And that should be all equal to my 500,000. Okay? Now actually what I have is I have this stuff in here being my geometric series. Okay? So actually I factored out the x, only the stuff in square brackets I'm concerned with now for a geometric series. And let's look at this. It has a first term of 1. It has a ratio of 1 over 1.003434. That is, we multiply by this to get to that. We'd multiply by this again to get to that, so on, so on. How many terms have we got? Well, even though this terminates at 299, we still have a first term 1 out on its own here. The second term has a power of 1 there. So we still do have our 300 terms. So filling in what we know here, we can say that S of 300 is equal to A, which is just 1. It's not going to do anything. 1 minus the ratio, which is 1 over 1.003434 to the 300, all over 1 minus 1 over 1.003434. So when I put that stuff into my calculator, what do I get? Well, on the top line I get 1 minus, and then I'll open a bracket, another fraction, 1 over 1.003434, and that's to the power of 300. And underneath I get 1 minus another fraction, 1 minus 0.003434 equals, I get this like 187.72. Let's go to 3. Let's go to 3 decimal places. So approximately this. Okay. Now I would highly suggest that you try this piece here on your calculator yourself and see do you get this number. A lot of the mistakes are made here. It's just simply people forgetting zeros. So I actually know now that 187.723 can replace everything inside the square brackets. That gives me x times 187.723 being equal to 500,000. I'm solving for x, so x must be equal to 500,000 divided by 187.723. What does that give me? 3 divided by my answer gives me an x of 2663.50. So we can see that from this I actually get a pension payment for 25 years of 2,663.50 using all this. So I recommend you definitely go back through that again and try some different figures and see if you get an answer that just makes sense in the right ballpark.